What's up, dudes? Can you hear my voice? Jillian can't hear my voice because he just left. Anyway, I hope that the audio comes through pretty soon. Here's what we're going to do. We're going to apply the quadratic equation. I really love the question that Tejas asked me yesterday. Jillian, can you hear my voice? I really love the question that Tejas asked me yesterday. Like, when I was tutoring him yesterday, he was like, why should I care? Like, what the heck is the point of this? Like, I taught him how to find the vertex, right? And he was like, oh, that's cool. I can find the vertex. And then he asked me, Mr. Dolday, why should I care? And I was like, you're awesome. Because you asked me a question. And I'm sure that, do you guys ever feel uncomfortable asking that question? Because I don't get it asked enough to me.
I get it.
You feel uncomfortable?
When, like, asking.
Don't be ashamed, bro. Don't be ashamed. Don't be ashamed. You just ask, hey, teacher, why should I care? And then what I would say is, okay, check this out. Take a piece of paper, crumple it up, and throw it like a basketball into a trash can. Do you see that shape that it made? The shape, the arc that it followed? That is called a parabola. In fact, most things, when thrown and under the influence of gravity, make out a parabolic motion. And finding the vertex would be like finding the highest point in the arc. Does that make sense?
Yeah.
Jillian, do you see what's going on? Like, where did the idea of all of this stuff come from? Well, I feel like a lot of it first came from the ideas of, when we had Isaac Newton and all of those guys. I'm sure that it was the parabola was well established before him, but back then, cannonballs were the in thing, right? Like, if you could tell me exactly where this cannonball landed, that would be kind of important. How long it's in the air for, where it lands, where it starts. And the cannonball is exactly following an arc. And that particular arc that it's following is a parabola. Now, I know what you're saying is, I've got Justice here who wants to be an electrical engineer. And Jillian, what is it that you want to be? What is it that you want to do? I'm just curious. Do you want to, I don't know if you can hear me. I'll talk while I wait your answer. But Justice wants to be an electrical engineer, so this might be a little bit more applicable. But even then, I feel like you guys are going to say, yeah, but Mr. Dalday, I don't know what I want to do, but I can tell you that I probably don't necessarily want to be an artillery specialist and calculate out these parabolas. So why am I learning this? Because this is applicable to people back in the old days when they were doing cannonball calculations and that kind of stuff. And I would say this. I would argue this. Okay, so Tejas, he wants to be a doctor, okay? And you need to balance out certain things. Like, for example, you need to balance out the amount of medicine you would prescribe to somebody. Because if you prescribe too much, or if you prescribe none of it, that's not good for the patient, right? But if you prescribe too much of it, that's also not good for the patient. So, I can easily see a situation where you have okay, well, let's say they take 2 pills a day, and this is the person's health. Let's say they take 4 pills a day, and this is the person's health that's at 35. They take 6 pills a day, and their health is still at 35. They take 8 pills a day, and their health is down to this is 27 or something like that. So there's this optimal range, right? There's this special amount that you would give this person per day or per week or whatever, so that they can be at the best health they could possibly be. And where would you get the best health from?
At 4 pills.
At 4 pills? Nope. I'd say at 5. Or maybe 5.5. No, this is 5, 6. Yeah, at 5. Right between 4 and 6, right? Because at 4 and 6, you're this much more healthy. Then at 4, you're over here.
Oh, so you would give them 5.
So you would give them 5 pills a day or 5 pills a week or something like that. You see what I mean?
Yeah.
And these curves exist all the time. So even though these curves, I mean, you can actually see a physical representation when you throw a football or a basketball or whatever. You can actually graph some of these things, and a lot of times they're very well-controlled graphs. And one of the most graphs that you see the most often is a quadratic or a parabola. That's why we come up with all of these crazy equations to get these very important pieces. You know what I mean? Like, you would want to know where the zeros are. You know why? Because this means 0 health. That means you killed the patient. So you would want to know, okay, that's my zeros. Right? You would want to know, that's where I can't give too much, I can't give too little. That's OD right there. Right? And you would want to know where the vertex is, because the vertex tells you exactly how many pills you would be able to give that person and how big their health is or something like that. I don't know. I'm just making up a situation. In electrical engineering, this thing pops up so much. Like, you would not believe. In fact, you want to know the crazy thing is? You know that thing? I'm teaching my son about, like, real numbers. And yesterday he was asking me, like, well, what's not a real number? And I said, well, I'm teaching this guy Justice over here. He wants to be an electrical engineer. I'm teaching him about imaginary numbers, right? It's what we taught you guys with the I, right?
Yeah.
That rears its head when you're talking about phase diagrams, when you're applying it to three-phase electricity, my friend. Like, imaginary numbers actually have an application in the real world, which trips me the heck out. But it works. And it's amazing. So, anyway, there is my justification of why you should care. You should care because this is the culmination of knowledge over hundreds and hundreds of years of studying. And we're giving this as a gift to you. Yeah, but Mr. Dolde, calculators can do the same. Sure, calculators can do the same, but there are things that you will learn eventually that calculators cannot do. Or you need to be the guy or girl who creates the calculator to do it. And in order to get to those topics, you gotta put in your time. You gotta learn the basics. This is the basics. Cool? Are you thoroughly motivated?
Yes.
All right. Then, I feel like a lot of this is review. Let's go through warm-up real quick, and we'll just kind of talk about these things. All right. Let's look at graph 3. Where is the y-intercept? Just look at the picture.
At 10.
At 10. Perfect. What's the x-intercept or septs?
11 and negative 1.
Negative 1, 11. In this case, there's 2. Now, a parabola can have 3 different types of intercepts. It could have 2 intercepts. It could have 1 intercept. Or it doesn't need to have any intercept. For example, number 4, graph 4. That doesn't have any intercept whatsoever. Where does the thing cross the x-axis? This being the x-axis. It never crosses the x-axis. I don't know why I went into that voice, but whatever. What is the y-intercept? Well, the y-intercept is like negative 22 or something like that. The disadvantage of using the graphs, of looking at the graphs, is that you can get a good ballpark picture of what the thing looks like, but you can't pull out specific numbers. All right, anyway. Does this graph have a maximum or a minimum? Do you understand what that question means?
The highest point on the vertex.
There is a highest point on this graph right here. Is there a highest point on this graph, on graph number 2? No. This thing goes up forever this way and up forever this way. What's the highest point it goes? Infinity. There is no highest point. It just keeps going. But on this particular graph, there is a minimum because there's a lowest point. So, positive facing parabolas have a minimum. Negative facing parabolas, because this is where A is negative, you take the regular parabola, you flip them upside down, has a maximum. Are we cool? Jillian? Can you hear me?
You are currently the only person in the
Oh, just left then. All right. Anyway, hey, come on close. All right. So check this out. Let's talk about the x. Let's talk about the y-intercept. What is the y? So I told you that, like, looking at a graph, you can pull out this information quickly. You can't get super accurate about that information. Like, what is the exact y-intercept here? I can't really tell because it looks like -22. It could be -21 or 23. I don't know. I know it's between -20 and -25, but I can't really tell. It could even be 21.375. I don't know. So over here, this is the same, or this isn't necessarily the same thing, but this is a different form of representing a function, a parabola, and in this one is the standard form. Now, what's nice about the standard form?
So you can just pull the numbers out.
You could pull out what numbers?
The A, B, and C.
The A, B, and C, exactly. The A, B, and C that you would need to apply the quadratic equation. Bada bing, bada boom. Also, what's really nice about the standard form, you can get the y-intercept real quick.
Yeah.
When you want to find the y-intercept, you just plug x equals 0. That's 0, that's dead. That's 0, that's dead. What's that? Y-intercept.
It's 7.
It's 7. Awesome. What is the x-intercept or septs? Well, what would I use for that?
The quadratic equation.
The quadratic equation, with a being -1, b being -6, and c being 7. What would the vertex be? How would you find that?
-6 over 2 times A.
Ah, good. You're doing the negative b over 2a?
Yeah.
So it's actually +6 over 2 times -1. So it is still going to be negative. That's going to be -3, right? And then how do you find that? That gives you the x-coordinate of the vertex. How do you find the y-coordinate of the
You
vertex?
plug it into that equation.
You plug -3 into there.
Into the standard form.
All right. I like it. I like it. I'm cool with that. Another way to find the vertex, if you were confused about that equation that I just threw out there, -b over 2a, I'm not exactly 100% sure I even showed everyone that. But all you would do is you take whatever x-intercepts you got from the quadratic equation, take the average of that, meaning add them together, divide by 2, and that should give you -3. Cool? All right. Jillian, you keep jumping in and out. I tell you what. Why don't we take a, you know what? Let's do this. I want you to write something down for me, and this is probably going to be the equation that you guys are. If you take physics, you'll see this equation so much. Okay? Latex equation editor. By the way, just to let you know, I'm not going to require this of you, but you might want to look into this thing called LaTeX. That's what I use. It's what I use to type all of this math up.
Okay.
But, I mean, you as an engineer probably don't necessarily need it, but I mean, it's very helpful to me. Especially since you're of the computer generation.
Yeah.
All right. Anyway, write this equation down. It goes delta x. Oh no, it's capital. Equals v sub 0 t plus 1/2 gt squared. Delta x equals v naught t plus 1/2. I'm sorry, not g, a t squared.
So it's 1/2 times.
A times t times squared, or times t squared. I guess if you want to put c dots in there.
Okay.
What was that?
It's a little confusing.
It is a little confusing. Please don't ask me where I got it from. Darn, I wish I could tell you. I hate when teachers pull equations just out of their butt and throw it up on the board and say memorize this. I'm not telling you to memorize this. I can actually show you where it comes from. Would you like to see?
Sure.
Oh man, why? Why would you want to see that? All right.
I don't know. It's interesting.
All right, fine. Well, here, I'll tell you what. Why don't we use this equation first? And then we'll use this equation first. Oh, wait, 1 second. Hello? Hi. It was sick. I was sick yesterday. Or the other day. Yeah. I don't know. Okay, I'll check it out. All right, thanks. Goodbye. All right. Let's write down the equation and let's talk about it real quick. Okay, delta x equals v naught t plus 1/2 at squared. You probably won't see this inside of your math book. You will see this in your physics book. They give you the baby version. The baby version that they're going to give you, I bet, is going to be something like this. H is equal to v t plus 4.9 or 16 t squared. Oh, sorry. I better put a... Okay. So I'm telling you to write down delta x equals v naught t plus 1/2 at squared. They're going to give you h is equal to vt plus 16t squared. It's the same equation. They just gave you the little baby version. All right? Now, since you want to be an electrical engineer, you're going to have to get used to this because you're going to spend a whole chapter in physics class doing this. I will show you today, because I'm such a nice guy and it's kind of a pain in the butt to do it, but I will do it anyway, where this equation comes from. Okay? But I will also show you where this equation comes from. Let's start off with this one. Let's talk about the different variables that they represent. Delta x, you read that together. That is not delta times x. Whenever you see this delta, it means the change in. So we're talking about the change in x. And usually when we talk about x, we're talking about the position of something. Okay? So we're talking about how far something is, the distance that something is. So when you're talking about the difference in x, you're just basically saying, what is the final distance minus the starting distance? Which basically is saying how far you travel.
Yeah.
Does that make sense?
Yeah.
So that's what all this is this delta x represents how far you travel. You should write this down. All right, v with a little sub-zero right here, v naught. That's what I called it. That usually means velocity initial. Sometimes people write vi, and maybe I'll do that for you just because, you're a little nervous about this. When we're talking about physics, at least the first year of physics, we often have two different kinds of V's. We have VF, which, what do you think that stands for?
Velocity final.
The velocity final, and we have VI, velocity initial. I like calling it V naught because that basically means the velocity at the beginning, at 0. That's why I call it V naught, and that's kind of that's how I learned it. T, what do you think T represents?
Time.
Time, very good. All right, what do you think the A represents? We're talking about movement here. So you have position,
Average.
you have speed, and you also have, or you have position, you have velocity, and you also have average. No. Think about racing a car.
Okay.
What are some of the terminology you would use? You would talk about position, speed, and
Acceleration.
acceleration, exactly. Now, the reason why I accidentally wrote a G instead of an A is because when we're talking about throwing things, the acceleration we're usually talking about is gravity. Does that make sense? And if you are measuring in feet, because you're an American engineer and use dumb measurements, you would say that g is equal to 32 feet per second squared. Got it? If you're a scientist, like the rest of the world, you would say it's equal to 9.81 meters per second squared. Meters per second squared. It's just a difference of units, right? You understand that, right?
Yeah.
Do you see now why they automatically put a 16 there? Because half of 32,
Is 16.
1/2 g, that's why they have a 16 there. I don't even know. I'll be honest with you. I didn't really look at this and and know this off the top of my, or like know that they did this off the top of my head. Let's take a look. Oh, look, it's a negative 16t squared. Oh my goodness! Like seriously, I didn't come up with that myself.
Yeah.
Actually, see what they said is, oh, you would use this as the A. The A is related to the constant acceleration due to gravity. And they said use 16 if you're talking about feet and use 4.9. No, that's BS. You should use 32 or 9.8. They built in that 1/2, and half of 32 is 16. That's why they say use 16. Half of 9.8 is 4.9. That's why they said use that. Don't get tripped up.
Okay.
You see what I mean?
Yeah.
I don't mind using their equations. I'm just letting you know where they come from. All right. Use this, because this is how you do it. That's not how you do it. All right. But look. Oh, by the way, why is it negative 16? Why do you think it's that?
I don't know.
Because which way does gravity go?
Oh, it pulls down.
Gravity goes down.
Yeah.
Hence the negative.
Okay.
Does that make sense? You see how this all kind of logically gets put together?
Yeah.
Is it kind of exciting?
Yeah.
Ever so slightly? All right, cool. Yes, absolutely. It is negative 16 or 4.9, depending on your, what type of, if you're talking about feet or if you're talking about meters. For now, let's just stick with their thing. All right, whatever. They tell you that this right here is your V naught, because that's the number in front of the T. Apparently, how fast was this ball moving initially? It's highlighted in blue.
80.
80 feet per second, probably. Exactly. Now, where did this T come from, or this 3 come from? Oh, whoa, what happened? Where did this 3 come from? Because it's not in my equation. There's no extra number added to that in the end.
Oh, no.
I'll show you, because it's a little complicated. I know. When I show you this, you're going to be like, wow, that's so trippy.
Okay.
Once I prove to you where these equations come from. Now, am I showing you am I showing you stuff that is good for the math class? No, I guess what I could do is I could just straight up take this thing and apply the quadratic equation and we'll go from there, right? But what I'm really trying to show you, especially you, because you want to be an engineer, is where all this, we're talking about where it comes from. Where's the motivation? Why should I care? Why should I do these things? Okay. So, this number over here comes from the delta. And I'll tell you why. I'll tell you what. Let's graph this. Let's go to Desmos and we'll graph that sucker. This is actually a really good lesson. I didn't even make homework for this yet. But this is a really good thing that we talk about this. Alright? This apparently is the equation they're telling us is the height of the ball at any given point in time. Okay? So, I'm going to write it down. Negative 16 t squared You know what? They don't like t. I'm going to use x because they don't know how to graph t. All right. Plus 80x plus 3. Now, I'm going to zoom out. Dude,
It's a skinny
that was
parabola.
not necessarily a good hit. I mean, seriously, wait, a baseball is hit in the air at, all right, fine, whatever.
It's straight
It
up.
apparently went 103 feet. Where did it land?
3 feet in front of him.
It landed 5.404 feet away from him. Dude, that's called a pop fly. You suck at hitting. Like, I'm looking at your thing and I'm like, okay, so the catcher had to walk 5 feet forward and catch the ball. That's probably been in the air. Actually, I can tell you exactly how long it's been in the air. 4. Oh, no. I made a mistake. It's not 5.4. It's been in the air for 5.4 seconds.
That's a long time.
Hello? I'm so sorry. I have to call you back. Thank you. So unprofessional, Mr. Dalding. All right. No, this was the time axis, right? The
Yeah.
x-axis was time. So it's been in the air for 5.4 seconds. We could figure out exactly how long or we can figure out how far it's gone, and that's another thing. But maybe not with the information they gave us. But it's been in the air for 5.04 seconds. Not very long. Very high up there. It went 103 feet. Now, where did it went? At what time? What did it reach 103 feet?
2.5 seconds.
At exactly 2.5 seconds after he hit it, it went 103 feet in the air.
That's really fast.
Well, he hit it at 80 feet per second. Now, where did that 3 come from? What is that 3? What is that 3?
The change in X, like I don't know.
That's the y-intercept,
It is.
right? Like when you let x equal to 0,
Oh yeah.
it's the y-intercept.
Okay.
What does that mean? That means the batter was 3 feet tall.
Really?
Well, no, not really. I mean, that means the batter hit the ball, and the ball started
At 3 feet above the
at
ground.
3 feet above the ground when it was hit.
So his hands were
Which
by
makes
his
about
waist.
sense because his hands were about his waist. You know what I mean? A 6-foot baseball player hits that ball, boom.
Yeah.
So I mean, it wasn't 3 feet tall.
Yeah.
I thought it was just funny and it would help you memorize it better. But
Okay. But now I understand.
essentially, yeah, that's what that means. It means that the ball started at 3 feet off the ground to begin with. Here's what they did. Now, keep in mind, you don't need this equation per se. But here's what they did. I'm just showing you how my equation differs from theirs. My equation is better, but how my equation differs from theirs. Remember what I told you about delta x? It's the change in x, right?
Yeah.
It's x final minus x initial. I'm going to put, instead of a xi, I'm going to put x naught. Is that all right? All they did was they added x naught to both sides. That's the same exact equation. This is the 1/2 g,
Okay.
because g is negative 32, and so 1/2 of that is negative 16, t squared. Here's the velocity initial, and here's the x initial. They're saying that the height final at any given point in time is equal to 1/2 gt squared plus v naught t plus 3. Now, let's apply some actual math to this. Let's let all the other students feel more comfortable with what we're talking about and actually see how this applies. Okay, fine. So here's the quadratic equation we're talking about. It apparently is h is equal to negative 16 t squared plus 80t plus 3. All right. What I'm going to do is I'll probably apply the quadratic equation to this quickly. I'll apply the quadratic equation to this so that even though they're asking me all these questions, there are pieces of information that are very important. First is the vertex. Second is first is actually the intercepts. Second is the vertex. Third is the y-intercept. Y-intercept in this case is very easy to get. It's 3. In this particular case, it means that, what does that mean?
That the ball started at 3.
The ball started at 3. Awesome. What is A, B, and C in this case?
A is negative 16, B is 80, and C is 3.
Perfect. Negative 16, 80, and 3. So when I apply the quadratic equation to that, which is negative b plus or minus square root b squared minus 4ac all over 2a. When I apply the quadratic equation to that, I get negative 80 plus or minus the square root of 80 squared, that's a big number, minus 4 times negative 16 times times 3, right? All divided by negative 32. All right, I'll plug that into a calculator. Let's see. You're going to beat me with the calculator because you're way better than I am. Let's race. Negative 80 plus square root 80 squared minus 4. Let's do plus 4 times 16 times 3. Close parentheses. Close parentheses again. Divide that by negative 32. Enter. I win. Did I win?
Yeah.
You gotta learn how to type. It's way quick. Huh. Negative 80 plus or plus the square root of 80 squared minus 4. I don't know if I did it right. Let me just check. Parentheses, negative 80 plus square root 80 squared minus 4 times negative 16 times 3. Enter. Alright, whatever. One of my answers is that. Let's try the minus. I bet you I know what's going on. It's going to be 5. Give me 5. Ooh, 5.04. I am so awesome. All right. The first answer it gave me, and I was looking at it, I was like, what's going on? The first answer they gave me was like, what was it? It was 0.04, right?
Yeah. I got 0.037.
Which is 0.04, right? Look at the x-intercept. Negative 0.04. Ha! Sucker! The next answer they gave me was 5.04,
Yeah.
right? Awesome. It's so smart. So, your answers are at negative 0.04 or 5.04. Those are the x-intercepts. Or in this case, we're calling them the t-intercepts because we're graphing this as a function of t, not x. Got it? This horizontal axis is the t thing. So this actually answers the question: how many seconds did the ball, or how many seconds did the ball finally hit the ground? After how many seconds did the ball finally hit the ground? 5.04 seconds. I guess you can ask, when is the ball on the ground? And your answer is at 5.04 seconds. It's also on the ground at negative 0.04 seconds. And that doesn't really make sense to you. So we throw that answer out because there's no such thing as negative time. See what I mean? A lot of times when you are dealing with quadratics, you get these things called extraneous answers. There is no such thing as negative time, so let's throw out the negative time as one of our answers. Because our other answer was positive 5.4. I don't know why you have a negative there. What is the maximum height that the ball reaches? Okay, well, to do that, you would simply just do... That's finding the vertex, right? So that would be negative b over 2a.
So it'd be negative 80
which is negative 80
over 32.
over 32. Figure that out for me.
80 divided by 32 is negative 2.5.
Which is... Oh, I'm sorry. It's not 32. It's negative 32 because a is negative 16.
So negative 80 divided by negative 32 is 2.5.
So, what is that? What is 2.5? It's right here.
Oh, the vertex.
Yeah, it is the vertex. Tell me what it means in context, though.
The maximum height ball reached.
No, it's not the maximum height the ball reached.
How many seconds it took the ball to reach?
It is the time in which it reached the maximum height that it was going to reach. Does that make sense?
Yes.
If you want to figure out exactly how high it went, then you take that time, you plug it into your function, and you should get 103.
You plug it in for all the keys.
You plug it in for all the t's. You put 2.5 here and 2.5 here. You square that, and multiply that by 80, and bada bing, bada boom, you should be good. Does that make sense?
Yeah.
Cool. So that's. Do you see how this is directly applicable to something in the real world?
Yeah.
I think that's cool.
Yeah. It is.
You want to know another, off the top of my head, a good use for parabolas?
Sure.
You know, telescopes?
Yes.
They shape the mirrors. You want to know how they shape the mirror?
By using a parabola.
It's a parabola. Isn't that cool?
It just looks like a flat surface, though.
Yeah, I know, because the really big telescopes, you don't want that big of a parabola. I mean, you want a huge parabola, so you're only getting this part of it. But I mean, if you continue it out, it's a parabola. It's not it's not a sphere. It's a parabola.
Looks just like a circle.
Anyway, I digress. Let's talk about this one real quick. A golf ball is hit in the air. Negative 16. Just by looking at this, tell me things that you can tell about this thing. Negative 16. What units must we be using? Are we using feet or are we using meters?
Meters.
Nope. We're using feet. Because remember, I told you, in feet per second squared, gravity is 32.
Oh.
In meters per second squared,
It's
9.8.
Okay.
And this number in front of the t squared should be half of gravity.
Okay.
Remember the 1/2 gt squared? So since I'm looking at 16, I know, they must be dealing with feet. Now, a true scientist, they would just give you that equation, delta x equals v naught t plus 1 half at squared, and expect you to accommodate for those things. These guys force feed you these equations. I hate when they do that. What does the 148 represent?
Far illicit.
No. Delta x equals v naught t plus 1 half at squared. So here's the t squared part. What did I say that was right in front of the t? Look at your notes.
Oh, that's right.
Nope, it's right in front of just the t.
Oh, the velocity.
Apparently, this golf ball was hit with a velocity initial of 148, meters?
Feet per second.
Probably feet per second squared because, or not feet per second squared, but feet per second because we're dealing with feet over here. We don't want to mix up those kinds of numbers. If we're dealing with feet per second squared here, then you want to use feet over here. Does that make sense?
Yes.
At what height was the golf ball when it was hit? I'm throwing that question out to you. I want to know what your thoughts are. How high was the golf ball when they hit it?
When they hit it, it would be on the ground.
Okay. So you're saying that it's on the ground when they hit the golf ball to begin with, right? I agree with you. But mathematically, look at it. What is the y-intercept of this thing?
0.
If you want to find the y-intercept, you plug t equals what?
0.
0. So you plug that in here, that gives you 0 here. You plug that in here, that gives you 0 here. So what is your height at t equals 0?
0.
0. Does that make sense? Yes, of course, because when you play golf, you don't hit it from 3 feet off the air,
Yeah.
in the air, unless you're Happy Gilmore and you throw it up in the air and then you hit it like a baseball, right? You hit it when it's on the ground. Maybe if you want to be super accurate, maybe you would put like 1/12 over here. And that would stand for like 1 inch off the ground because
The tee.
technically it's on a tee.
Yeah.
But who knows? Maybe this thing started off on the grass.
Okay.
You know what I mean?
Yeah.
Does that make sense?
Yeah.
What is the maximum height that this ball reaches? Or what is the maximum height this ball goes to when it I'll just ask the question. What is the maximum height of the golf ball that the golf ball reaches? How would you find that? Think, my friend. Think about it. I'm going to get rid of some of these equations right here.
You find the vertex.
You find the vertex. Very good. Which equation should we use to find the vertex?
The quadratic equation.
We could use a quadratic equation. That will give us our 2 intercepts. That's important stuff. What's another way we can do it?
The vertex down that you do.
Yeah, that one at the bottom. Dude. Hello? Hey, what's up? Yeah. Actually, I'm in class. Can I call you back? Okay. Oh no. Are you going to drop off the kids? Okay. Today is National Bike to Work Day, and they have a big event. I mean, across the nation, everyone's in it. So I bike to work. I thought I had to leave really early to get there, so I left at like 5 this morning. But I got to work at like 6:30. So I was pretty surprised because usually I can leave to catch the bus at 6 o'clock in the morning, and I get to work at 7 o'clock. But if I leave, with the bike, it only took me an hour and a half. Instead of going down, the hardest part for me would be to figure out how to get across Cam Highway, right where we live. So what I did was I went over to Waikele, and then I went down there and did all the surface streets over there. So I didn't have to go on the freeway or anything. So I biked a little bit further, but I basically did a bunch of bikers were passing me, and like they were like hardcore bikers, and then I guess my idea was like, all right, I'm gonna go as fast as I can safely go. So even if it takes me, even if I have to detour around or through Waipahu, I'll go and do that because that's safer, No. Yeah. Yeah, I biked to work today. You got an ear infection? Okay. You might want to make a doctor appointment then. Okay. Well, I'm sorry you're sick, Mama. I love you. Bye. My wife is wondering why I left an hour earlier. Yeah. Because I bike to work. All right. Anyway. Yes, you would use the negative b over 2a, and you're already starting to do it. You did. I'm sorry. It's important that I answer some phone. It's important to talk to your wife when she wants to talk to you. I'm just letting you know. I know I wouldn't do that normally, but I'm just saying. Negative 148 divided by negative 32. What did you get?
4.63.
4.63 seconds. Awesome. So, is that our answer? What is the maximum height the ball reaches? No. That is the time in which the ball reaches its maximum height. Got it? Now, how do you find the height that it's at?
You plug in 4.63 seconds.
Exactly, there we go. You just simply take the original equation and replace all of your t's with 4.63. Because this equation right here, this above equation, will tell us the height at any given time. You tell me what time you want, I'll tell you the height it's at. And then you're saying, well, I'm interested in the time 4.63. And I'll say, okay, well, in order to do that, you just take it, square it, multiply it by negative 16, add 148 times that 4.63, and you should be good.
So you have to square this, you square the 4.63 first, and then multiply negative 16?
That's the way PEMDAS works. Please excuse my dear Aunt Sally means exponents before multiplication. Negative 16 times 4.63 squared plus 148 times 4.63. What'd you get?
Hold on, I'm still doing it.
You're still doing it.
Yeah, I'm slow.
Learn to plug the whole thing into your calculator one time. Actually, that's you got 343?
Yeah, for this one.
Oh, I see. Oh, and then you have to okay, all right, finish off. Go for it. I get 342 as the final answer.
Where would you get?
342. 342.29 something, blah, blah, blah.
You just gave me 342.2.
Oh, okay. You know why I gave you 342.2? Because what you did was you figured out this answer, right?
Yeah.
Which you ended up getting negative 343 or something like that.
Yeah.
And then you figured out the second answer. And then you added it together. But when you figured out the first answer, you didn't write down all the numbers.
No, I just did negative 343.04.
Yeah, but it's supposed to be 342.9904. You see what I mean? So what you did, and this is actually very relevant for you, Mr. Engineer, is you rounded off the answer here, and then you did this, and you rounded off the answer for this, and then your answer was rounded off in the end. Now, if you did here, oh wait, if you did the whole thing where you basically just plug this into the calculator and plug this into the calculator doesn't round off. You know, it doesn't take the time to write it down on a piece of paper and then too lazy to write down all the numbers so it rounds it off.
Yeah.
It just accounts for all of these things. So which one is more accurate, your answer or my answer?
Yours.
Mine's. Now, this is a really important lesson for you, Mr. Engineer, because you're going to build bridges. You want those bridges to be accurate. You want to make sure that screw is in the right spot and it's not off by an inch here or there. So, Mr. Engineer, please don't build a bridge that I'm probably going to drive over one day and kill everybody. Because and if you do, don't say I was your math teacher. You bet I'm like, I don't know that guy.
Okay.
All right. Anyway, you're right. It's 342. Technically, it's 342.2496. Now, we can teach you about significant figures. We're not going to do that here because that's not a math thing right now. That is more of a science thing, but that is your answer. All right. So here's the other question. How long did it take for the golf ball to land? What would you do?
Square 4.63.
Square 4.63. I like where you're going with this. It's wrong. I like where you're going with it, though.
It took 4.63 seconds to reach the maximum.
Uh-huh. I like where your brain is in the right direction.
Would you do the same? Would you add it?
To what?
Would you add 4.63 to 4.63?
So add 4.63 plus 4.63?
Yeah.
That's also known as multiply by 2. Right?
Yeah.
Okay. Yes. Yes, you're absolutely right. That is genius. That's brilliant. Let's graph this thing. You told me that it took 4.63 seconds to get to its final height of 342.25 feet. It's going to take another 4.63 seconds to come. If it takes 4.63 seconds to go up, and we're not including air resistance here, okay? Because that's a whole different kind of complicated math. Then it's going to take 4.63 seconds to come down from its final height, from its maximum height. So yes, you are absolutely right. To get this answer, you simply double the time that it takes to reach the vertex.
Okay.
I love the way your brain works. But it only works for this problem. Because I'll tell you why. Because the height is at 0, 0. Because it started at 0. That doesn't work in our first case. Over here.
Yeah. Because
2.5 if it took exactly 2.5 seconds to get there, then you figure that it would take. It would hit here at exactly 5, because twice 2.5 is 5, but instead it hits here at 5.04.
You have to take into account that he hit it 3 feet off the ground.
Yes. So, technically, the most accurate way to solve where this thing lands, or at what time this thing lands, is to apply the quadratic equation. In this very specific case, where the thing started on the ground, you can just take the time that it took to get to the height, or to the maximum height, and double it. Does that make sense to you?
Yeah.
But very good. I'm surprised, actually. I mean, I'm not surprised that you got it, but all right, I'm surprised that you got it. I'm surprised that you came up with that. I'm glad though. So, if you're confused about the discussion we just had, just apply the quadratic equation to that, and you'll get. What did we get before? It was. Oh, oops. It was 9.25 seconds or something like that. Cool. I'll tell you what. All right, here we go. In football, when a player punts the football, he hopes to have a long hang time. A hang time is defined by the amount of time the ball is in the air after it's kicked. If the hang time is longer than 4.5 seconds, it's considered good. If the punter is punting upward at a velocity of 80 feet per second. Now, what's the velocity initial? No. If you're reading this problem, what is the velocity initial?
80 feet.
80 feet. That's why it's the thing that goes right in front of the T. And since we're dealing with feet per second, we know that the gravity is 32 feet per second squared, or 32 feet per second squared. So half of that is 16. And why is it negative 16?
Because of gravity.
Because gravity is what?
Pulling down.
Because gravity pulls down, right? He's kicking up, so it's positive. Gravity's pulling down, so it's negative. And the ball started.
2 feet off the ground.
Why did the ball start 2 feet off the ground?
Because it's standing.
Nah, it looks like it's a punter. I don't know if you know football.
No, I don't.
But if it's a kickoff, then he puts it on a little stand.
Oh.
If it's a punter, he kind of tosses the ball in front of him and kicks it.
Oh, okay.
You've seen that before?
Yeah.
When he tosses the ball in front of him and kicks it,
Yeah.
it's higher off the ground. Apparently, it's about 2 feet off the ground. Does that make sense?
Yeah, that makes sense.
So, immediately, you look at this equation, you can pull out all of this information. What is the hang time of the ball? You can't tell me that by just looking at these numbers. But what you would do is you would say, all right, let's apply the quadratic equation to that. What's nice is these numbers are very similar to all of these other ones.
Yeah.
The only difference is, let's see, negative b is negative 80, yes. 4 times, okay, the only difference is I'm going to change that to a 2 instead of a 3. Because this is, this was from way back when.
Yeah.
And this is the negative b, here's the b squared, minus 4ac, and c is 2. By the way, why did I have plus 4 times 16 times 2 instead of minus 4ac?
I don't know.
Because I'm taking into account, I could either write this plus 4 times 16 times 2, or I could write minus 4 times negative 16 times 2. If I want to be technical about it, I should write this, 80 b squared minus 4 times negative 16 times 2. But what I did in my head was I just said, I'm going to account for that, because this negative times that negative is going to give me a positive. So I'm just going to put a plus there. Does that make sense?
Yeah.
All right. So that's one of my answers. The other answer is, if I put a minus here, 5.02 seconds. So, what's the hang time of the ball?
5.02
seconds.
Okay.
Was this considered a good kick?
Yes,
Yes. Why?
because it's above 4.5 seconds.
Good. Awesome. You're reading the problem. Okay. Suppose the same football player kicks the ball with an upward velocity of 48 feet per second. So what does that mean? I changed this to a 48. So a little bit more than half of what he kicked to begin with.
Yeah.
What's the hang time of the ball?
3.04 seconds.
3.04 seconds. Is this kick shorter or longer than the original kick?
Shorter.
Shorter. Awesome. Is this considered a good kick?
No,
Why not?
because it's less than 4.5 seconds.
Awesome. You know what? I'm almost... Man, I wish... Pass me that thing right over there. Yep. This is a cannon.
Really?
It has a metal ball inside.
That's good.
The trajectory of this cannon, this mini cannon, is governed by this quadratic equation that we're learning. As a lab, I'm almost tempted to just sit with you today and shoot army men
Okay.
from the thing. Does that sound interesting to you?
Yeah.
Yeah, Mr. Baldy, that sounds great.
Sounds fine.
All right, maybe we'll do that. That should be fun. All right, let's talk our way through the rest of these because this isn't hard. I mean, I don't think this is hard. This is just applying what we learned. This is like my favorite chapter. Now it is.
It's fun.
All right, here we go. Suppose the height of a baseball was thrown upward. This height, ht, is in feet per second, or t seconds later, given by this, negative 16 t squared plus 66 t. All right, what's the velocity initial of this thing, of this baseball?
66.
66. How high did this baseball, was the baseball at time 0?
6 feet off the ground.
6 feet off the ground. That seems a little suspect to me, but when I read the problem, it's thrown upwards.
Yeah.
Which kind of makes sense, because if you put your hand above your head, you could be about 6 feet.
Yeah.
So you release the ball 6 feet off the ground. Makes sense. What about that negative 16? What's the deal with that?
That's the feet per second.
Good. That is not feet per second, that's feet per second squared. That's gravity.
Feet per second squared, okay.
Now, look at this equation. I'm not even going to read the thing to you, but look at the equation. Negative 2.55 t squared plus 66t plus 6. It's kind of the same baseball story. Where is the velocity initial?
66.
What is the height at which it was
6
things?
feet.
So it's the same person, all right? But what's the deal with the negative 2.55?
I don't know. It's confusing.
Why is it not negative 4.9 or negative 16 or something like that? What is that information telling you?
That it's in meters.
No. I'm going to tell you now that it's still in feet because we're talking about the same baseball player.
Okay.
So it's still 6 feet off the ground. It's not 6 meters. That would be a very extremely. That would be a 12-foot person if we're talking about 6 meters off the ground. So,
Okay.
no, it's not in meters.
Okay.
This is significantly smaller than 16.
Yeah.
That must mean that acceleration is smaller. That must mean that gravity is smaller. What's the deal with this problem? Well, let's read it. Now, suppose the same athlete was picked up to be an astronaut. His first mission on the moon is to throw the same baseball with an initial velocity. Because gravity is different on the moon, we had to modify this term. Ah. So, well, no, I know we should have read the problem, but what I'm saying is I wanted you to take a look at this and say, gravity is funky here. We must be on some kind of planet. I mean, this is kind of thinking outside of the box, mind you. We must be on some kind of planet where gravity is not the same.
Yeah.
That's exactly right.
Space is like barely any gravity.
Well, in space there's barely any gravity, but in on the moon there is gravity, and it's very small.
Yeah.
Really, all of this stuff's the same deal, man. And here is, like, because I know you guys are thinking to yourself, like, you know what? I know we're going along, all right? Class was supposed to finish like 20 minutes ago, but I'll tell you what, I'm having fun with you,
Okay.
and I hope that you're hanging with this.
Yeah, I like it.
This quadratic equation stuff doesn't only apply to throwing a baseball. It applies to, and I think this is really important. Kaimi opens up a bakery and is going over the business model, and he realizes that his daily profits, PC in dollars, from the sale of C wedding cakes is given by the formula PC equals C negative C squared plus 100C. Okay, so this is the amount of money he makes is given by this equation. I wonder why it's not a straight line. Because you figure that if he makes more cakes, right, he would make more money. You figured it would just be a straight line relation. Make more cakes means make more money.
Yeah. But sometimes, like, if you could have leftover cakes and then it could go to waste.
Ah, I like it. I like your idea. If he makes too many cakes, he might not sell all of them. Then he's losing money.
So then that would be a parabola.
So that could be the reason for it the more parabolic shape instead of just being a straight line. Also, keep this in mind. Think about this. Make more cakes means more money, but it also costs more money to make more cakes.
That's true.
Right? The material you're using, the flour, all of the sugar, all that, because that's not free. No growing on no trees.
Yeah.
I mean, if you're selling mangoes, which literally grows on trees,
Yeah.
then yes, sell more mangoes, get more money.
Yeah.
That's true. Because all of that stuff was free for you.
Yeah.
But if you're talking about, like, you had to buy the materials and that kind of stuff, then if the more you make,
The more you're spending.
the more you're spending to make them. Now, the more you make also means the more you sell.
Yeah.
So, you have to find balance with this thing. And in finding balance, let's talk about that. In fact, I'll tell you what, instead of rehashing it through the quadratic equation, I'm going to, at this time, go into cheat mode, where I'm basically just going to graph this thing. Negative x squared. I'm going to change it to, instead of a c, I'm using x. Because Desmos doesn't like
Anything but X.
Yeah, it doesn't like anything but x. Ooh.
That's a skinny parabola.
No, it's not a skinny parabola.
It's not. Oh.
It's just a big parabola. What is the maximum amount of wedding cakes he should make in order to maximize his profit?
50.
50 wedding cakes. If he makes 50 wedding cakes, I guess in that month or something like that,
Should make 2,000.
then he should make $2,500. Sweet. If he makes more than that, like 56 or 50,
He's losing money.
if he makes 60 wedding cakes,
Yeah.
you're only going to make $2,400. You're losing money. And that trips me out because you're thinking, well, why is that the case? Well, maybe you can't sell all of them.
Yeah.
You're going to lose money.
Or
Also, maybe you're making too much and you need to...
it's going to waste.
It's
and
going-
you're still wasting money on trying to make more.
Yeah. Or if you made 40, you would still make $2,400. Why?
Because you have no leftovers.
Because you didn't make
Yeah.
enough, and everyone probably bought up all of your stuff. And if you made more, you could probably make more money.
It's better to sell out than have leftovers.
No, it's not better to it's not better to have leftovers. It's not better to have too little either.
Yeah.
It's better to learn math and learn how to find the vertex of a parabola and get the just right part.
Yeah.
Right? Not too hot, not too cold, but just right.
Yeah.
That's what you want.
Okay.
I mean, if you're not going to be an engineer, and people watching this video, I don't know if they've lasted this long at this point, but people watching this video, they're like, I'm not going to be an engineer. Yeah, but you like money.
Yeah.
Money is important. Does that make sense?
Yeah, I get it.
So do you see how this stuff comes like
In the play.
into play? It's very useful. I'm very. I guess we talked about this. What does it mean if Kaimi sells less than 50 cakes?
Yeah.
It means
Less money.
less money. What happens if they sell more?
Less money.
Less money. Why? Well, there's a lot of other factors that go into it, you know, and we described two very good ones. I love the ones you came up with. I've never taken an economy class, econ or whatever. I was not a business major, so I'm sure that they have other things that you have to consider, like, you know, advertising and what about if you have to, like, you know, I mean, here's another good idea. If you want to make, you know, like 100 cakes, why are you not making any money? Well, think about this. What if you made 100 cakes and in order to do that, you had to hire more people?
Yeah.
And they had to work. You had to hire them not just part-time, but you had to hire them full-time.
And you have to pay them.
Then you got to pay them. And when you hire them full-time, then you got to take into account their 401k, their health insurance, all of this kind of stuff, and pressure, and I don't like being a boss and all that kind of stuff. But I mean, like, there's these things that govern these shapes of these graphs. So we're not talking about your good old lemonade stand that you made when you were a kid. Just like, I sell more lemonade, I get more money.
Yeah.
We're talking about real business here.
Yeah.
Now, if this were, I sell more lemonade, I get more money, here's what the graph would look like.
Straight up.
It would be like this.
Yeah.
Sell, make, sell, make, sell, make. You know, you just make more money and more money and more money. Does that make sense?
Yeah.
But that's only the case if you're talking about getting free materials.
Yeah.
It doesn't cost you anything to make it.
Your parents are providing.
Your parents provided it, and they didn't sell you the lemons.
Yeah.
You know what I mean?
You went and picked your own.
Yeah. And they're like making it for you. You don't have a job. You don't need to do nothing. You can just stay home and make lemonade all day.
You just get money.
Because you're 4 years old or whatever. You just get money. That's sweet. That ain't the real world, but it's sweet.
Yeah.
Does that make sense?
Yeah.
All right, cool. We finished this whole freaking chapter. I mean, I shouldn't say that word, but I'm just saying we finished the whole darn chapter, and it was good. All right, stop recording.